Hello, my name is Brett and welcome to the second part of my videos on the RC522. In this video, I hope to give you a better understanding of the RC522 and the RFID chips that you'll be working with. Let's jump in right away with an example. What would happen if you used a complex chip to read? I'll be using this Amiibo to showcase the differences between RFID chips. Unfortunately, an Amiibo is read-only, so I can't display the problems with writing. Hopefully this section will help you understand what's going on inside an RFID chip a little better so you can customize your code to work with your specific chip. So let's see what happens if we try reading our Amiibo using the read test we just made. As you can see, we get what is called an auth error. Every RFID chip has an authentication code. Simple MFRC522 assumes that the authentication code is the same standard general code across all RFID chips, but our Amiibo has its own unique authentication code. That means we cannot use simple MFRC22 to read data from this Amiibo. Well, what if we forego the authentication process by writing our own code? I have already written code here based on the simple MFRC522 code, where I do not authenticate. So let's see what happens. Running the code, we can see that we can indeed read the Amiibo. Great, so no problems, right? But we actually run into a different issue now with our original RFID tag. Running the code again and using the RFID tag this time, we can actually see that we get a reading error. This is because with this specific tag, we have to authenticate in order to be allowed to read with it. I have a different code here called read with auth, which is basically the same as complex read, but now it has the authentication process. So now if we run this code with our RFID tag, we can see that we are actually allowed to read it again. If we try this read with auth code with the Amiibo, we see that we run into the exact same error as we did before. Well, that's fine, you may say to yourself. I can just write proper catches and exceptions to combat this error. Well, that may be true. There is another problem you should be aware of when working with the RFID reader. Let's take a look at this for statement here and understand what is going on in it with our data when we are reading it. What the code here is doing is it's checking blocks for data that has been written into the RFID. Think of the data in RFID as a matrix, rows of blocks with 16 columns, each column holding a piece of Unicode data. But if RFID data is indeed matrix-like, why do we start at block 8? Shouldn't there be readable data in blocks 0 to 7? Let's see what happens when we change our code to check an earlier block. So here we're going to check at block 7 as well when we read. Let's try that out. And as you can see, an error while reading occurs that breaks the entire system. This may be due to the fact that we are not allowed to read from that point from a design standpoint of the chip, or it may be because there's nothing written there. If it is indeed because there's nothing written at block 7, let's try writing something to block 7. So let's use this alternate write code, and let's try writing some data into there. So we're just going to write a mess, and then we're going to press enter, and we're going to place tag. And you can see that we actually get another error when we try and write to that location. What happens if we try and read data after block 10? So let's read from block 11. We can see there's actually data inside block 11. However, it's not something that we had written inside. If we were to try and write to this block, we would get the same error as when we tried to write to block 7. I believe this is because the designers of the RFID chip put important data important to the functionality of the RFID chip inside of block 11, so they did not want people writing inside of it. If we continue from block 11 to block 12, we can see that block 12 won't cause an error, but there's no values and nothing can be written or read from it. Everything after block 12 will repeat the same errors as that occurred in block 7. Now, why am I bringing this up? Well, let's try doing something similar, but with the Amiibo. Let's just read from block 0. And now if we read from block 0, you can see that we do actually read data. So this brings up the question, how many blocks does the Amiibo have, and how many are readable? After some research, I found that an Amiibo has 16 readable blocks. So let's try reading all of those blocks. I'm going to change the code a little bit here to do the range of from 0 to 15. And so now if we run that code and we do our read, you can see we get a much longer written code, and you can see that we actually have 11,176 characters squeezed into that. It's a lot of data. I want you to think about what would happen if we were actually allowed to write to the Amiibo. Would we be able to write to every data block? Which data blocks are my written data and which are holding data for the functionality of the chip? The reason I brought all this up is so that you can understand that every RFID chip is different, has its own set of rules, and can hold different amount of data. It'll be up to you to test your chip and change your code accordingly to get your RFID reader to properly read and write to the chip. Thank you and best of luck with any future projects using the MFRC522.